A high-traffic Java API is operating smoothly until peak load hits. Within minutes, P99 latency spikes from a stable 120 milliseconds to 4 seconds. Incoming requests back up across the network. Thread pools exhaust their capacity. The infrastructure enters a state of cascading failure. During a crisis of this scale, engineers check standard observability dashboards to locate the bottleneck. Because the service is halting, memory exhaustion is the primary suspect. This dashboard highlights a diagnostic conflict. The left latency metric forms a vertical wall, while the right heap usage graph displays a stable sawtooth pattern. Seeing regular heap drops, engineers often assume garbage collection is healthy, investigating database locks or network saturation instead. But the database and network are functioning normally. The actual source of the latency is the JVM garbage collector, specifically the internal work it must perform to account for objects that remain in memory. Basic heap graphs are insufficient for diagnosing severe tail latency. True performance engineering requires penetrating deep internal JVM telemetry to see what standard charts obscure. When faced with latency spikes, a common engineering response is to apply random JVM garbage collection flags, found online in hopes of a quick fix. Altering collection parameters without investigating the application's underlying allocation behavior rarely solves the problem. A new flag might delay a pause, but it cannot release an object the code continues to hold. The most effective tuning strategy prioritizes code. Addressing application-level object retention must occur before attempting to optimize collector performance through flags. Garbage collection tuning is a sequence of auditing allocation behavior, bounding data retention, and matching the collector architecture to specific service-level objectives. To understand retention, we must define how the JVM calculates what memory is safe to free. The collector operates on a model of mathematical reachability. The calculation begins with GC roots. These are the anchors of memory, consisting primarily of active thread stacks, executing frames, and static fields. This network models reachability. Top nodes are GC roots. Lines are active references keeping objects alive. Dropped references break the connection, leaving orphaned subgraphs eligible for collection. If a path exists, the object remains live, regardless of business logic. Memory leaks in Java are rarely unreferenced memory floating in a void. They are actively referenced objects that the application has not yet released. Modern JVM architectures are governed by the generational hypothesis. The vast majority of newly created objects die young. A web request generates thousands of short-lived objects, JSON parser nodes, stream pipeline buffers, and data transfer objects. These should ideally never survive a single collection cycle. This partitioned container shows the JVM heap structure. Allocation and immediate destruction occur rapidly within the young section. Objects that survive multiple sweeps trigger a promotion mechanic, migrating across the boundary into long-term storage in the old generation. Specific data structures belong in this old generation. Connection pools, singleton beans, and application caches are designed to persist for the lifetime of the process. A healthy collector exploits this separation. It sweeps the young generation frequently at low CPU cost, while deferring the more expensive old generation sweeps for as long as possible. Returning to the 4-second latency incident, we bypass the dashboard graphs and inspect the raw, unified GC logs to establish a factual timeline. The raw logs reveal 3 critical warning signs: abnormally frequent young collections, a massive allocation rate, and continuous old generation growth. These metrics distinguish between 2 distinct states: memory pressure and a true memory leak. Compare these old generation baselines. Left, memory pressure. The heap rises but returns to a flat baseline. Right, a leak. The baseline steps incrementally higher. Our incident matched the right side, proving indefinite object retention, explaining the excessive CPU consumption. To inspect this retained graph, engineers generate a heap dump, using the dominator tree to map the exact path from surviving objects back to GC roots. Standard monitoring tools measure the symptom, which is latency. Analyzing the retained old generation baseline and the dominator tree isolates the cause. The dominator tree identified the specific structure driving the retention, a customized metrics tag cache, originally designed to hold lightweight diagnostic payloads. The cache design contained a significant flaw. It possessed no maximum size limit and no eviction policy. Once data entered the map, it stayed there indefinitely. Because the application tracked high cardinality labels, storing raw URLs and unique user IDs, the cache key space exploded in direct proportion to production traffic volume. The 4-second pauses resulted from the garbage collector repeatedly scanning this massive, permanently referenced structure, mathematically failing to reclaim memory during each and every cycle. Resolving the leak requires immediate code-level changes. Implement a strictly bounded cache capacity, define an eviction policy, and strip all high cardinality labels from the metrics registry. Only after the code is patched and the old generation baseline stabilizes should an engineer evaluate heap sizing. Over-allocating heap size as a temporary measure can degrade performance. Excessively large heaps lead to longer worst-case pause times and generate slow heap dumps during emergencies. In containerized deployments, the JVM heap represents only a fraction of the total required memory footprint. This diagram represents a container limit. The Java heap occupies only a portion. The remaining boundary accommodates direct memory, metaspace, and OS caches. Failing to account for this is risky. Unchecked direct memory can breach the boundary, terminating the process. Correct JVM sizing demands a view of the entire process footprint. The container boundary must be large enough to encapsulate all JVM overhead, not just the heap. The final phase of tuning is selecting a garbage collector architecture that matches the system's service level objectives. Parallel GC is an effective choice for batch jobs and offline processing, where maximum throughput is more important than temporary pause times. G1 GC is the standard for general server workloads, using a region-based heap layout to balance throughput with predictable pause targets. Specialized collectors like ZGC and Shenandoah are engineered for massive heaps and strict P99 latency requirements. The sub-millisecond pauses of ZGC require an operational trade-off, consuming more concurrent CPU work and requiring careful sizing to maintain necessary processing headroom. Collector selection is an engineering choice between throughput efficiency and tail latency predictability. An optimized, stable infrastructure operates in a state of high-performance equilibrium. Achieving this state requires a consistent production checklist, enable unified GC logs with rotation, ensure heap dumps trigger on out-of-memory, and strictly bound all data structures. Engineers should monitor the post-GC heap baseline rather than the overall heap maximum to identify slow-burning leaks before they impact the user. Garbage collection is a highly observable mathematical process. When paired with disciplined systems engineering, it yields perfectly predictable performance.